So in this video, we're going to use our position vector that we defined in the previous video, RAB, in order to determine the components of a force that's directed along a line or from a single point to another point. So if we have our position vector RAB, we know we can calculate the unit vector UAB using RAB divided by its magnitude. If we know we have a force that also goes from point A to point B, what we can do is we can say that that force from point A to point B is equal to its magnitude times our unit vector UAB. Okay? So this is really useful in engineering systems that have pulleys or ropes or cables, because often the anchor points of those cables are known. So if you know where the start of the cable is and the end of the cable is, and you know what the tension is, you can then determine what parts of the force are being applied to that point, or like the components of the force that are being applied to that point. So what we're going to do now is we're going to use an example problem to calculate what is force FB as a Cartesian vector. So the first thing we need to do is we need to calculate what is RAB. Alright, so we know RAB is going to be equal to RB minus R of A. Okay, so first off we're going to start with RB. Alright, we know that RB is going to be equal to, if we look here, it's equal to 4 meters times 1/2 of a meter. All right, so that's this, and it's going to be going along the negative x-axis. So this is RBX here. Then for the y component of RB, that's going to be equal to 4 meters times the cosine of 30 degrees, which is radical 3 over 2. All right. And then for the z component, RBZ, that's just going to be equal to 3/5 times the length from the origin to point B, or 3 meters. Alright, so I'm just using the information on the diagram to calculate the x, y, and the z coordinates in Cartesian form. So we can repeat. So R of A is much simpler. Its dimensions are just given to us, so we can just write R of A is equal to x of A, which is just equal to R AX, that's going to be equal to just 2 meters. There's no component along the y-axis. Alright, and then there's just a small z component. Alright, which we can write as being also 2 meters. Alright, so following our formula, we can just subtract our x components and our y components and our z components to get RAB. So if we do that, we're going to subtract minus 2 meters. So you should get minus 2 meters, I, plus 4 meters, radical 3 over 2, minus 0 meters, j, plus 3 meters, minus 2 meters, k. All right. So if we do all the math, what we end up getting is we get minus 4 meters, I, plus 2 meters, radical 3, j, plus 1 meter, k. All right. All right. And then, so once we have RAB, we need to calculate the unit vector. So we can say that, so we know that the unit vector from point A to point B is equal to the vector RAB divided by its magnitude. So we need to calculate what is the magnitude of RAB first. So the magnitude of RAB we know will be equal to the square root of the sum of the squares. So we'll just square each component of RAB. So we do 4 meters squared minus 4 meters squared plus 2 radical 3 meters squared plus 1 meter squared. If we add that all up, we get 16 meters squared plus 4 times 3 is 12 meters squared plus 1 meter squared, which is a nice ugly radical 29 meters. Okay, so then we can divide our x, y, and our z components by radical 29 to get UAB. So we would get UAB would be equal to minus 4 meters divided by radical 29 meters I plus 2 radical 3 meters divided by radical 29 meters times j plus 1 meter divided by radical 29 meters times k. All right. So we can now that we have UAB, we can write FAB. We know is the vector FAB is the scalar product of the magnitude of FB. Sorry, this should be not FAB but FB. It'll be equal to magnitude of FB times UAB. So we were given the magnitude of FAB was equal to FB. The magnitude of FB was given to us as 750 newtons. So we're just going to multiply 750 newtons by each of our position vectors components to get our components of our force B. So if we do that, we'll end up getting force B is going to be equal to minus 557.09 newtons I plus 482.45 newtons J plus 139.27 newtons K. Alright, so we can round that to 3 significant figures if you'd like. And our answers would be minus 557 newtons I, 482 newtons times J plus 134 newtons times K. All right. So just to summarize, if you're given the magnitude of a force and you're given the coordinates of its start and ending point, you can calculate that force as a Cartesian vector by first determining the position vector from the starting point of your force to the ending point of your force. Then you can take the once you have that position vector, you can determine its unit vector by determining first the magnitude or the length of that position vector. And once you have that length, you can divide each of the components of the position vector by that length, and you'll get the unit vector from that point to the point where the force starts, the point where the force ends. And then you can then multiply that unit vector by the overall magnitude that you were given, and you can then solve for the x, y, and the z components of your force.